All right. What I'm going to do here is, in fact, go back a few slides and talk about that the RGCA, Reliability Growth Cause Analysis, because now is probably an ideal point. Let me go back to where we talked about that. This step here of understanding the parts and the risk the parts carry. This is in the workbook. And what we've got here, I'm just taking a simple, a part out of a machine. This particular part is the valve. This exhaust valve, I've just said, here's the technique we take. In this engine, some of these parts will do far more work than other parts. We're going to look for the parts where the stress is. The parts that are under stress are the ones that we're going to find. So I'm not going to worry too much about this issue here. That's simply bolted on there. The procedure needs to be written so that this is properly done, but this won't be under stress. That part will be under stress. Any moving parts, any parts that rotate, the pump internals are going to be under stress because they're being used. So I'm not going to do every single part because I can. I'm going to do the parts where the risk is to the machine. So out of 200 parts, there might be 24 in the end that I will actually analyse in some detail. So I've taken the exhaust as an example of what to do. We want to create the reliability block diagram of that situation. We want to create this thing into a process flow diagram, if I can get the right direction. So my exhaust valve is modelled as a process flow diagram, now, because that's how the machine is built. It's built as a whole series of parts, in this case 200 parts in some sort of reliability block diagram. So here I've got my exhaust valve, and what I want to ask is, for each of these activities, where can the stress come from for that part? And this I need to bring up a little bit. So I've taken the valve number. I've talked about where it is in the process. Heck, what's going on here? I need to reduce that a little bit. Come down here. Okay. Painful. All right, talking about a particular part, we're talking about the effect of that failure. If that exhaust valve fails, what's the effect on the engine? Will it impact the rest of the system? Now, if one item fails and it has no impact, then maybe that's okay, letting it break and because there's no knock-on consequence. But if there's a knock-on consequence from the failure and the engine's destroyed and the truck's out of service for 2 months and the truck's not making any money and there's business consequences. I need to understand, is there going to be a knock-on consequence? This particular diesel engine is actually the fire water pump in a fuel terminal. This is not the same diesel engine could be used in a truck, but in this case, it's a fire water pump driver. So if this diesel engine does not work when it's needed, there's a risk of burning down this whole terminal. So this particular bit of kit is critical stuff, critical kit. So in this case, the tank terminal could burn down because the engine that's meant to pump the water through to put the fire out doesn't work. So if this engine was in a truck, the risk to the business is much less, possibly. If this is the business's only truck, then it might be a very high risk for the business because it's the only truck they've got. Though they could hire a truck in the meantime, which could be a strategy they put into place if need be. So yeah, we have to understand the scenario the equipment's in, because if this particular machine fails in this situation, they could lose their entire terminal and kill people as well, of course. Now we're going to ask what are the costs of doing this? This still needs to be a little bit smaller. If we do not do this, well, what sort of costs are involved? In this case, $500,000 or $500 million is the sort of cost involved. what money is saved by maintaining this thing properly. If to protect against this, we're going to have to strip this thing down on a regular basis. It's going to cost $25,000, which over the service life of this machine is $500 a year. So I can now justify what's the cost of caring for this properly versus the cost of not maintaining this properly and leading to a breakdown. So there's serious money here. There's not a lot of money to spend to protect the business against a real serious disaster. It may never happen. You know, this may never happen in the 50 years of this plant, but the risk is there. And that cost there of $500 million, $500 million is a very high risk to live with and do nothing about. So on my risk matrix, that would appear in the extreme risk zone. Now, that if I don't do anything, it's going to sit there, and all I'm hoping on is luck working my way. A very difficult way, an impossible way to run a business, counting on luck for things not to go wrong. So my risk matrix, I'm going to say, well, what do I do to get that risk down to acceptable levels? And it will be things like doing the regular maintenance required, ensuring the condition monitoring is done to make sure that the temperatures are properly controlled, make sure there's no blockage of the cooling system. You know, all the things that keep engines running properly, we've got to do those things. Not kid ourselves that we can get away with that. We've got to do it on purpose, proactively, to prevent the risk of this arising. So where does that risk come from? What sort of situations can cause our stress to occur on our particular part? Let's go down a bit further. So one of the failure modes will be the seats can be burnt. If the richness of the fuel is the wrong consistency, they will actually burn the seats. And you'll hear of burnt seats in engines all the time. Very common problem. So we're going to prevent the seat burning. What's the frequency of that problem? Well, from industry, we can imagine some sort of scenario of in 1,000 hours of operation, the chance in 1,000 hours is certainly there. In 2,000 hours, the chance will increase. So the issue becomes, okay, what will it cost if that happens? I'm out for a month. On this critical pump that saves the plant from burning down, I can't be out for a month. This pump cannot fail. This engine cannot fail. What's the cost of supporting that and maintaining it? Not a lot of money to do that. Where can the degradation come from? As it's being used, this particular valve will be exposed to the risks. So it's during use of the machine that the valve is in danger of failing. What are we going to do to prevent that particular problem? Well, we can look at replacing the valves on a regular basis. We can ensure we do the maintenance required to protect the machine from failing. We may even want to mount some monitoring to check what the temperatures are during operation to make sure that it is not getting too hot. So we're going to put in place the things, we're going to recognise the things that prevent the stress in the first place. Once we know what we need to do to stop that stress, we're going to build that into our maintenance procedures, into operating practices. And all that stems from the fact that this cause is a real possible cause. What other failures can occur? We can have timing errors. That valve can be burnt from timing errors of the ignition sequence in that engine. So what's the chance of that happening? If it does happen and we destroy the valve from mistiming, again, we're down for a month. The costs will be the rebuild of that motor, $25,000. We expect that to happen possibly once in 50 years. This terminal will have a life. Typically 50 years is a reasonable life for a fuel terminal. The chance is there that this might happen once. The reason it'll happen once is that we have not yet protected against it happening. So if I don't protect it, then the odds are there that we won't learn of our mistake until we actually burn that fuel valve, until we burn that valve. So I'm expecting if we don't do nothing, then chance will go against us at least one time in 50 years, from which we will learn the mistake we have made by not protecting against it. So I've allowed for worst case one event, because we haven't protected against it, because it'll happen if we don't protect against it. And on down we go. For failure mode 2, what can we do to prevent failure mode 2? Now, none of these things are going to be new. The guys know timing's an issue. We know that valve getting hot will burn the valve and damage the seat. So we're not finding any new problems. What we're saying is these problems are real. They can happen. If they happen on this machine, it will be a high risk situation for the company. Because it's such a high risk, they cannot be allowed to happen. Then I must put into place the requirements so that it never happens. And the justification is, now we know what to do because each mode is recognised. Now I've got to write the procedures and operating practices to prevent these problems. So though everybody knows these are situations that arise, we have not yet put a cost, should they arise in this company, on this motor, in this scenario of a water pump in a fuel terminal. That's different scenario, different risks to this motor in a truck fleet of 100 trucks. Yeah? So what? This valve burns in that particular situation, so what?
What is that new matrix rating, likelihood 1, consequence 3?
Yeah.
What was the old one? I mean, what was the
previous one without doing that?
Yeah.
It's off the side, unfortunately. Yeah. We have got a column of the current risk. There's the numbers we get off our risk matrix. So it is there. That we want to have that process. Definitely want to have a before and after. Because it's only the before and after comparison that justifies doing something.
So the likelihood went from 3 to 1.
Yes. And again, you would want to show that visually on your matrix. That's the whole... There's a lot of detail here because I have to defend my recommendation to make the change. And I've got to be sure that in my head I actually believe that this will make a benefit. And I show that thinking eventually in some sort of scale, some sort of risk matrix and some sort of dollar value, but I can't hold my hand on my heart and say, Mr. Manager, I believe I'm right and here's why, until I have a good analysis. So yeah, it's fairly demanding on the person doing the analysis to be very clear about the real situation. And if it's really a high risk possibility, then we have to recognise that and then come up with answers, proactive solutions. In the end, what will happen with this particular machine, we're going to have very good procedures on how to maintain it well and how to operate it well, and possibly condition monitoring. We're going to introduce, if necessary, some sure ways to make sure that the mixture, the lean richness of our fuel is correct. We're going to make sure that the timing is correct. Because if timing will burn the valve, if a lean mixture will burn the valve, they cannot be allowed to happen. So what will I do to prevent mistiming, to prevent wrong settings of the fuel-air ratio? Because they will happen. Huh? You see cars with black exhaust coming out of the exhaust pipe. That's the wrong air-fuel ratio. Someone set that or didn't bother correcting it properly. So these are things that happen on real machines. The trouble is it can't happen in this machine, in this situation, because it could lead to complete loss of the fuel terminal. And that's what we try and do.
You know, one thing that'll change that ratio that most people don't think about, I didn't think about it until it happened to me. If you have an engine that's been running for a while, a few years, you don't have to have anything wrong with the valves. The actual bolts that hold the head onto the engine can slightly loosen and suck air in from the side and change the ratio. Just slightly.
Yes, enough.
Change enough that it will turn on your check engine light.
So another failure mode, number 3, would be heads come loose.
And they can't just tighten the bolts. They, of course, have to take it off, replace the gasket.
Yeah. So if that is a possibility with an engine, a diesel engine, you wouldn't want to walk past that. May happen once in 100,000 engines, but that could be the 100,000th engine that it happens on. You don't know. That's what risk and chance is all about. This particular engine, you have no idea what will eventually happen. But 1 in 100,000 engines will have that very problem, and it could be this one. And is that an issue I'm willing to live with? At $500 million, no. For $500 million risk, I'd be happy to go there every 3 years, go and redo my head gasket every 5 years under controlled conditions.
Or I would tell them to get standby redundancy, get another engine.
In the real world, what happens in a fuel terminal, you've got to have two driving pumps. You've got to have two units to drive, electric one and a non-electric one. Because if I lose the power during a fire, electric motor stops, I've still got to fight the fire. The diesel fires up. So in a fuel terminal, electric pump is your prime pump that fires up first because it's easier and quicker to do that. But your standby is the diesel.
You know, it'd be interesting to see a risk analysis of the nuclear reactor in Japan that shut down
After the tidal
tsunami.
wave.
Reactors are supposed to be loaded with backup diesel engines. None of them worked. There's got to be a reason for that.
Oh, yeah. Well, it'll be a business process failure of some sort, but the consequences are huge. Yeah. So I guess I don't want to be pulling teeth on this. The point is I don't want to do this for anything that's unimportant. So we want to find what parts are at risk of failure, what's the consequence if they do fail in this scenario situation, and if it's too big a consequence, are you going to live with it or not? Mr. Manager, tell me what to do. Can't live with it? Okay, well here's my recommendation. Here are 15 things you need to do in your business process to protect against this, including every 5 years putting a new head gasket in. Because I don't know if this is number one out of 100,000 motors. Or I can monitor. I could introduce some onboard monitoring to look for change in fuel-air ratio. There's probably a monitor, you can install that on the side and it can begin monitoring continuously. And there are smart answers out there. The thing is to recognise where the risk is first. Because if we can't see the risk, we'll do nothing about it.
Which is, it's easier to monitor for that in a car, so you ought to be able to do it anywhere. If that's one of the things that triggers the check engine light is a bad ratio.
Yeah. So we don't want to invent something new, you just want to recognise, hey, we've missed a really key, dangerous issue here and we have to address it now and proactively forevermore. So that's reliability growth course analysis. If I fix these problems, I will create reliability. I'll actually prevent things going wrong. The part won't fail, the machine won't stop, the plant is safe, and the business doesn't lose any money. I think that in fact was a change, wasn't it? That we're into a different step now. So I went back to talk about our planning to decide how to select where the danger is, what can cause that danger, and then what to do about that danger. Now, we want to then take those decisions that we've made in a financially based decision process into practice. Because I have done many reports of recommendations, and the report stays on the shelf, never put into practice. So we want to make sure that companies, when they recognise the danger, and we make it very clear the financial risks and the financial benefits they're going to gain, that they will actually do these things because it's smart business to do it.
Now, when they don't do it, why do you think that is? Because they aren't really convinced there's a financial consequence? They doubt it?
Look, risk is like that. I mean, a fire may never happen in this terminal, but around the world every year, a terminal goes up. One or two terminals around the world go up every year. Now, it may never happen in 100 years on this terminal, but on the terminals on the planet, I guarantee you'll see a fire regularly across the world of fuel terminaling. The manager of this plant will say, never happen here because of my best practices, my trained people, my procedures. I'm going to say, you show me your procedures, let me plot that risk and see what holes you've left. Because it's the holes they can't see that convinces them everything's okay.
I think of that incident many years ago in Bhopal, India, where Union Carbide accidentally released some cyanide gas and killed a zillion people outside the
Over
plant.
2,000.
That incident shut down Union Carbide. Union Carbide no longer exists because of that incident.
No, and it's exceptionally rare that these terrible things happen, but they do. Around this world, they do. You don't know whether it's your terminal or the guy in India or the guy in the States or the guy in Europe. You don't know. You're counting that what you've developed, that the process you have got is going to protect you. But we know our processes are built by people, and people are not perfect. And things degrade, and machines degrade, and businesses degrade, and people retire, and a new guy comes in who hasn't been trained properly, and now I'm in danger, and I don't even see it because I think my current procedures are sufficient. All right, the next step in the 6 process steps for plant equipment and equipment wellness is to look at how to introduce these changes. We've already talked about scripting what needs to be done. So in the end, it's going to be document-based. We use documentation, and by documentation I mean a written word, and that can be in a computer, can be in a hard copy document. The whole point of writing things down is we are designing a process. This whole activity of coming up with what to do is a design philosophy to build a designed process done a certain way, as a consequence delivers a certain outcome. So I want to build a process and design it and select how it works and select the techniques to use and select the tools to use and select the training to use, that when I run that process, my distribution is always a known range of outcomes. And I want to have the distribution well within inside my boundary. So whenever that process runs, it will always produce what the process is designed to produce. So this whole activity of going through these 6 steps is to come up with a blueprint, a design of the way to run the business, the way to run the machine, the way to run the maintenance processes, the way to do condition monitoring, that when we do it this way, we know what's going to happen. Same as Boeing. We follow Boeing's documentation. We follow their procedures to the letter, because Boeing know if you do it to the letter, you will get safe planes that people will use. So the thinking is no different to what we know works. We've got to turn this into something that every company can adopt, every company can justify financially is worth doing. So we've got to the point where we've found the risks, decided which ones we want to deal with and minimise, come up with an understanding of how to achieve that. Now we're going to put those designed ideas into a designed process to actually make these things happen. So we're going to introduce the controls into the business. Again, there are some simple steps, some simple intentions we're trying to achieve. We know the duty output we want. We want this machine to last 5 years trouble-free. In fact, we'd like to have a machine that over its entire service life never fails. I'm going to maintain it in a way that prevents failure, operate in a way that prevents failure, so that over the 25 years it is failure-free. Not maintenance-free, still got to look after the condition of my parts. But I've now got a way to look at the stress in my parts, come up with a design methodology to minimise that stress, build that into how I run the machine, maintain the machine, select the machine, and in theory I've now got a process that I will run for the next 25 years and produce a failure-free service life, maximum availability, least maintenance cost. That's our intention. Now the world's not perfect, so we're going to accept that things can happen, but we're trying to minimise the unknown and design something that produces the results that we're after. So we've got to an idea of how to do that. Now got to turn an idea, a concept, into practical work. Same as a movie. I write a script. I review the script. I practice the actions. I practice the play, and I refine that until I know this off by heart. Then we run that known practice and expect those known results. Everything's going to come down to a document because we have nothing else in the world yet that beats that approach. I suspect one day we're all going to have computer connections to the back of our head, and then the computer will talk to our brain. They're actually working on that now. It isn't there yet, and it won't be there in our lifetime, I suspect. So at least for the next few years, few decades, paper is all we've got. It's worked fine for a long time. The point is we're going to have to design that process, and that will be on some document. And from that document, we go into creating the business that works that way. So we're going to write specs for our equipment in terms of its maintenance, its operation. Without that, what happens is we still run the machine. We can run a machine without any documentation. We're going to learn how to run the machine by breaking the machine and fixing it. And that's a hard way to learn how to run a machine well, to break it first, then fix it and break it a couple more times till I realise, hey, that will actually break the machine. I better change my practices. We want to get past that step because in doing it that way, it's a very expensive learning process. So from what the machine's meant to perform, we're going to turn it into the activities the operations guys, the maintenance guys, the engineering guys, the project guys, the finance guys will actually do. that will come into a database. The way we decide to design our processes and run them and build them will be a database. Everybody goes to the same book every time. So those documents you write are universally applicable and be easily available in a computer form. That also affects the training required. Once I know what I want to do, because if I do it right, I get this outcome. But I've got to do it right. So until we get it right, I'm going to train people and retrain people. And if it's too hard, I'm going to try and find a simpler way again and challenge guys, look, we've got our first cut pass of what we think is acceptable, but I will take your advice. If you've got a smarter way to do it, we're going to have a look at that as well. So I want my 100 guys doing it one way, with 100 brains looking for better answers. And that's part of the continuous improvement that we want to see in a company.
Who do you visualize writing these the first time? That's a good question.
Someone that knows the engineering of the machine, knows the process and what the machine's doing with that process and what the machine's changing the process to.
But don't they have to be written so that a somewhat uneducated person can follow it?
It's got to come down to that, yes. In my mind, I would imagine probably an engineering level person. Would have to be someone that is competent in the machine's design, the machine's operation, and the process that this machine is converting things to. So it wouldn't have to be an engineer, but it has to be a person that knows what is right and what is wrong.
And they have to be instructed not to write this so only fellow engineers can understand it.
Yeah. And this is why it's a refining process. Some engineers are going to be very technical and they're going to be absolutely right in what they put down, but it's not transferable across to the guys that will run the machine. So we're going to have a transferable solution to the lowest level guy in the business that will run that machine.
What if the customer says, well, I don't have any engineers to spare, why don't you write it? Is that a viable?
Well, bear in mind his people and his resources in his company, he might not have the technical skills, but the guys have been running the plant now for a while. I'd be working with them all the time. You'd have to have a first cut pass and say, well, look, here's what I think's happening. Or you'd go out and do some research first, work with the guys, ask them questions, have a look at their history, go back to the OEM, the original equipment manufacturer, and ask, how is this meant to work? How's the design operating? So I'd be learning from what they're doing, then applying that knowledge on my first draft and go back to them and say, well, look, let's work together and refine this right down to a document you guys will use. So the final guy that gives the nod is the guy that will run with that document. Me as an engineer, I'm happy at a high level of technical input, but he will need a lower level. But it has to be right. We want a process that produces the right outcomes. And if my process is so difficult and it's so engineeringly complicated that my guy running the machine can never use that document, then I have built a bad process. Though it might meet an engineer's satisfaction, it's a bad process for the operator of that equipment, and he's got the final say. It's the only way to be sure that what we are introducing will be used. And wherever possible, we want to get the guys that are in that place right now to work with us, because they have to own that solution, because they're the only guys going to do it. I'm never going to have a manager come down and kick this guy off his machine and take over and run this machine for the next umpteen years as his job. Not a manager's role to come down and run that machine, but the operator's role for run these machines. So we have to have him buy in and want to do this the right way. So he's going to have to be involved in putting in the things that are correct for him to do. Bear in mind, this is like any machine. When I buy a machine, the designer has gone through a complete design process. There's been blueprints, there's been prototypes, there's been revisions, there's been model Mark 1, model Mark 2, and there's going to be continuous development of the original design. This is no different. These documents are live documents. We're looking to make things simpler and smarter. I've just got to start somewhere. Now, once I start and we run the process as it's intended, it will improve itself. Again, same story. The game we're playing is to minimise variation into a known outcome. And I've got to design a business documentation that creates a process that delivers these results. It's what businesses are all about, in fact. This particular slide is a good snapshot of what the game is. This is the game we're playing. We're playing a game where we are in control and capable. Every process, whether it's a human process, a mechanical process, a electrical process, a financial process, anything I can do box and arrows with, I can turn into a process. And the game is, if we're out of control, then we've got a business that is an unknown outcomes. In this case, every month, the first 3 months, every month, I cannot predict what's going to happen. A lot of scraps being done here, some good product. Next month, I have no idea what's going to go on. Now, out of control is what that situation's called. So we say, look, we consider problems, let's come up with some improvements. Give me some suggestions, let's make the changes that have to be made. Next 3 months, we are now in control. I can predict the future. Still making scrap, still not there yet, but we are now in a control situation. I can tell you in 2 months' time, if we do it this way, we're going to be within this boundary. In this case here, our boundary is a very big distribution, and we're well outside our spec range, but it's going to be month after month predictable. It'll be in that distribution. But we are making scrap, which is a waste of money, waste of time, waste of effort, and that isn't any sense in that. So I want to change and improve the business to this final phase here, being capable, in control and capable. Now everything we do is right because I have achieved a process change that produces a known output that is in the range that I want. Now for me to play this game, what's the very first thing we must have? Very first thing I must have to start this game and actually look at making the right changes to achieve the outcomes we're after.
Data?
You need information.
Of what is right. Yeah. The first thing we need is to know what is right. What is the specifications, what are the standards we must meet? So the first thing that goes down is a standard. Give me the tram lines. Put the tram lines in and I can adjust my process until the outcome finally comes in to where it should be. And I'll keep experimenting, testing, challenging, questioning, looking for smart solutions, quick solutions, cheap solutions that are right for the business because I know what I've got to produce. And until I produce that religiously every single time, I'm not there yet. But I know when I am because I always am within the required outcome. So that's the game business is all about. That's the game we're playing with Planet Equipment Wellness. What is the standards that will deliver the quality, that produces the reliability, that will give us failure-free service life for the length of that machine's operation? The story doesn't change. The tools and the techniques and methods to achieve that is what we want to find, bring into the business, make it normal practice. So reliability is normal practice because that's how we run the business. Everything we do creates reliability. All our training creates reliability. All our decision making creates reliability. And that's how we've built the business. And we're not having reliability now. This business is producing those results because that's how it works. You work the business in that way, you only produce out of control situations. Change a process to this one here, and because we've changed the process, you will get control. Still not capable. I've got to keep changing my process until the process outcome produces that. And the process decision is the critical decision because it's the process that we use that produces those outcomes. And until those outcomes are where they need to be, we're not there yet. Now, the thing that we want to do is write all these documents, which nobody likes. Everybody hates having to sit down and write them. Everybody hates to use them. But right now, there's no other way known on this planet to bring control to a process except to design it, model it, draw it up, write the documentation, specifications, parts ought to be ordered, manufacturing processes and maintenance processes written up. Then I have a designed process. There's no other way we can do it at this stage. I cannot do it. I cannot do it in as much as I won't bother about the effort. That decision will produce those results. It must do. You have no controls. You will get no control because you haven't built it into your process. So I don't see any shortcuts but to sit down and go through this and do it well. Take the time to do it well. If you do it well, you're going to get the results you want. So once we design this process and we have the documents, we want to lock it into place. We want to make sure that this is never forgotten, that it's how we will do business forevermore, and we will improve that intentionally with strategies to challenge for better solutions. And that's where the accuracy controlled enterprise comes in. The accuracy controlled enterprise begins with standards. Those tram lines are the first things we have to decide. How good do we need to be to produce those results? And if we aren't good enough yet, well, that's okay. That's part of how we're going to grow the business, how we're going to improve our people and improve myself as well. So it's a quality management system. ACE3T is a quality management system, not ISO 9001. ISO 9001 is a quality management system as well. This is a different approach. Still document based because we have nothing else, so we have to have written designs and written plans. But we're going to be driving the business towards the outcomes that produce standard known outputs. And we're going to use the tools that are already in use across the world. We're not going to invent new tools. We're going to try and use the tools that everybody's used to and are comfortable with, but with a different focus. With a focus that we want that result. Give us that result every single time as quickly and as smartly and as cheaply as possible. But always the quality comes first. So yeah, we are refocusing and using what we know in a way that has a clear intention of producing certain outcomes. So now my plan, do, check, act concept of experimentation and testing an idea fits in with improving the business. Because our first script will not be perfect. But by the 7th or 8th script, we're going to be pretty good. We want to create lasting reliability in our machines by stopping these problems starting. I don't want to fix anything. I can fix that. It's a software. I can fix a software. Vibration, I can fix that. Gee, out of balance, I can fix that. I can fix all of these. But now I've got maintenance. Now I've got breakdown. Now I've got years and years of nightmares. I don't want to go there because we don't have to go there. We can stop these problems starting, and that's what wellness is in Planet Equipment's wellness. I'm going to be around for 80, 90 years. I don't want to be sick at all. So I've got to eat well, got to sleep well, got to exercise, I've got to watch my diet, I've got to make sure that I don't have too much sugar, a whole bunch of things that if I do across my whole life, I expect to have a comfortable, happy, well, satisfying life because I've done the right things that produce the right outcomes. Same here. These problems are because the wrong things are being done. And the consequence is these failures. Stop them from starting by doing the right things that prevented it in the first place. And the answers have been there since 1985. 25 years have been around. This is not something that is impossible to do. But we just aren't getting them done in companies.
And Deming or somebody said, every process is perfectly designed to give you the results you're getting.
Absolutely.
Which I thought was pretty good.
Yeah. Well, he's being honest. He's saying, what process you run, you're going to fall somewhere in those areas there.
But so many times over the years, somebody will say, look at what's happening. Why?
Yeah. No,
you designed the process.
Yeah. And that's the bit managers can't see. They don't realise that choice produces those results. And it's the choice you've got to change. The results come from that choice. And if we make bad choices, so we want to have a technique that makes good choices. And plant wellness is all about making good choices because they will then give us what we're after. This was seen before. In our work activities, many tasks, many opportunities to go wrong. Same with our machines, same with our business processes. This makes it pretty clear where any trouble arising will lead to a problem. So, yeah, the flowchart image is a vital part of understanding and doing the analysis. One of the things that we're going to front and have to confront is the fact that maybe our organisational structure is a poor selection. This particular structure here, the silo and hierarchical structure, was actually invented by the Germans to fight wars. And because it was there back in the days we began inventing machines and inventing businesses, it was natural to bring a military structure into running organisations because that was the sort of thinking at the time. The trouble is, this sort of structure we focus on particular issues that are very, very narrow. Whereas plant wellness is a life cycle requirement. You know, from the beginning concept to the eventual disposal. We've got to look across that whole life to get the maximum return on profit across the life. So when it comes to maintaining machines, we have to understand who's doing what job, who's responsible to use the machinery. Well, typically it's the operations guys on the shop floor. Who knows about the machinery? Well, typically it's going to be the engineering and middle management. So right away, the guys that run the machines and the guys that know what the machines are meant to be doing for the business aren't the same people. You've got two different focuses in different parts of the organisation. Who knows about the process? The production guys and, again, the middle management guys. The operations guys that run the machines that make the process to create the product they're making don't understand the process of the conversion. No, they're just running a machine. They don't understand that there's, to run the machine well and get the results the company wants, things you've got to think about and be aware of. And on we go. Who's got the knowledge of the equipment? Well, the machine knowledge is with maintenance. Often with supervision of the larger workforce, not with the guys that actually run the machines. So we've got a function, we've got a dysfunctional structure. We've got a structure that segregates knowledge. The information is distributed across a whole bunch of guys in different silos, and the machine itself suffers, and the plant suffers, and the process suffers because no one place with the right answer. The right answers are everywhere, and nobody ever brings them together into a common process that produces a known output. So hierarchical structures may not be the best choice for a company, even though all the books talk about them. You go to MBA and they talk about organising your business in a certain way and setting up different levels and different control mechanisms. And I'm saying, well, hang on guys, this is where we are today in this world of business and industry. After 200 years, here where we are today. That must be because everything we've done in the past has got us to where we are today. And if today is a bad, lousy place to be, and you're not happy with it, then it's because the processes this company's got, including the way it's built itself, produces today's performance. And I've got a question. Do you understand that this might be the problem? That the way we've actually structured the company may have to change to make a better world in the future. And what we're finding now in ISO 9001, when you go and have a look how they built ISO 9001, they talk about a process structure, about building a business that produces the process outcomes the business wants to deliver to its clients. And they say, look, this hierarchical structure, if it's in place, should be refocused in this approach here. There's a mission management focus, a clear direction to go and the purpose we're in business. But there's a product realisation to make the stuff that we want to sell. There's a resource management, the assets, the human beings, the finances. And there's a demand management, the sales and marketing. And 9001 is suggesting, look, the focus needs to be in these areas here. So we don't have silos that are independent of each other. We have people perhaps in that structure, but with a focus now that delivers these results. So everybody's focus becomes product realisation, whether you're in engineering, whether you're in production, whether you're in marketing. So begin to force guys together as a team with a common intent to produce a damn good product our customers love and keep coming back again and again and again for. And we go and market to people that value this product. And we use our resources and our skills and our capital assets smartly to get maximum return on investment. And not just, I just do engineering here, or I just do marketing here, or I don't care about the product and how it looks, I just want to sell it to somebody for the best price I can get and forget about the fact that it makes so many defects. We get so much returns and warranty problems that nobody wants to buy our product. So no, that's the issue we've got with this. We create small-minded people when we need broad-minded people.
You know, there's another interesting aspect to that makes me think about. There's a book called Learning to See, put out by the Lean Enterprise Institute, that talks about even within operations, you have isolated activities that don't really talk to each other, they depend on some MRP software to tell them how much to produce. And they basically say, you need to throw that stuff out and rethink this whole process.
Great challenge, absolutely. We have brought into solutions that someone suggests is better than what we know and take them on board and run with them as best we can, but never measuring the value of doing that and whether it actually made the place a better place to work or not. The consultant comes in, his job is to give us a new answer. We get a new answer, that's his job, he gives us a new answer. We just adopt it and run with it, but is it really the right thing for the business? Never go that far to find out. In the book, when I put the book together, I came across this idea of challenging our structures, our business structures. I also do 9001 consulting. I help companies develop their quality management systems to control the outcomes and outputs of their business. And 9001 doesn't give you answers, it just says we want these things to happen and you choose yourself how you make them happen. And one of those is how do you organise your people to get some value out of that. So I wanted to just put some mathematical investigation into what structure pays off the best. And what I realised when I had a look at our hierarchical structure, it's actually a series process. It goes from shop floor to supervisor to manager. As the decision comes back this way, the question goes up that way. So we actually built a structure that is sequential in the way it operates. So I thought, well, okay, let's look at what chance there is of things occurring as we would like to see them. Now, what we know in an average company, they're typically in the order of 2.5, 3.5 sigma outcomes. So I had an idea of what this little business would do on an average company, between about a 3 sigma error rate. That's what I expect typically what companies deliver until they get into serious quality control systems. So I began to say, okay, well, for me to get 3 sigma output of the business, I've got to start with an error rate of my people at 0.7. So I've just said, look, and I'm just playing with numbers here just to try and put some meat into this idea of what's the best structure to use. So I said, okay, well, these 3 guys are in a process. This person feeds him his work, this person feeds him that his work. So we've got a series process of making whatever this particular product is. So I've got a sequential process of 3 steps. Each person is a step, and we know they must be making errors of about 3 errors in 10 times to get to the 3 sigma output for the whole business. So I've got the reliability of this particular level. I then say, okay, well, in a series process, I can model the effect of the supervisor. So here I've put the supervisor in parallel. His job is to be in parallel with his work crew. Now, this is actually a work group. But his function in this setup is to be overviewing and double checking and monitoring what these guys are doing. So he's in parallel with his work team. So model in parallel, and this system of 3 guys produces a reliability of 0.8. So 80% of what they do is acceptable to the standards the company requires. Then I say, well, hang on, manager is in parallel with supervisors as well, because his job is to monitor and observe and instruct supervision. So he is acting as in a parallel activity. So when I do that, I get an output of 15 in 100. So around about the 3 sigma output of the total system. But what interested me was the difference these people make. When I put a supervisor in parallel in this sort of arrangement here, his effect on the performance of the outcome of that whole group is a huge factor in the total result of that operation. Same with the manager. When I put him in parallel in a silo structure, he is a huge factor in the success of that silo structure. So I've got a business where 2 people in that business make a massive difference to the performance of that business. The manager, supervisor. And if they are wrong, if they make the wrong choices, misunderstand the process, misunderstand the way the business is meant to work, don't understand anything about quality control and reliability, then they have their decisions, their position puts the company at huge risk of many things going wrong. So it gave me an idea of modelling a business in terms of the chance of success of this group and of that department and of that company. And the chance of success is dependent very much on the supervision and management level, because that's the way this particular structure works. And if I've got people in those roles that are not very good in those roles, the business will perform badly because their input has such a huge effect on what the business does. Then I say, okay, let's look at what the Japanese are doing. They're creating workplace teams. And so what's the benefit of a workplace team? So in that case, I've changed the structure to this one here. Now we have a team of 4 people. The supervisor is part of this workplace team. He's not called a supervisor. I've left it the same name to be able to explain where it comes from in the previous design. But this team now is running with a accuracy controlled enterprise approach. So the error rate per person, because we have a properly designed process the guys are well trained to do, the error rate comes much, much better. So we go from 0.7, 3 errors in 10, to 1 error in 10, because we have procedures and training and good feedback to the guys as to how they're going. With him as a group, we have a very high chance of success. We go from a 0.7 to a 0.97 chance of success with him, working as a team. He is not bossing anybody. He is guiding, providing assistance, providing advice, bouncing ideas off people, training them up, encouraging them to follow the design process. Then I add in the manager. And when I add in the manager, he makes very little difference, because this team is full of experts. This is a team of guys that know what they're doing. They can solve their own problems. They have information moving across through each other. They bring information in. This guy can go out and search for information. So this structure here produces a high chance of success compared to this structure here, where the chance of success depends upon 2 guys. So interesting, whether this is actually accurate in the way I've modelled that, but it reflected what I see in the real world. I know that if I have a lousy manager, that department doesn't go so well. Things go wrong. My supervisor doesn't understand the process of managing people and running that business. He'll make bad choices, and they flow through to bad outcomes. So it reflected what I'd seen in industry myself across my career. So I began to think, well, maybe there is something here that explains why a silo structure is a poor decision, whereas a team, an autonomous team full of knowledgeable guys, very powerful. So the Japanese concept of teamwork, hey, to me, the evidence is very clear. The chance of success is so much greater in a knowledgeable team full of guys that know what they're doing compared to a silo structure full of guys that maybe don't know what they're doing. So I'm going to suggest, if we're going to go to companies and challenge them about improving their business, then knowledgeable teams, or autonomous teams full of knowledgeable guys that can solve their own problems, I want to go there. I think there's real value there. And of course, when I'm doing a job, if my job is to do a particular task and I'm part of a team, then I can call on for help. Fred, I'm not sure what to do here. What do you suggest? And Barry, what do you suggest, mate? I want that interaction. I want to bounce off each other. And what Fred and Barry knows, eventually they will transfer to me. And I will then know in time what they know. So to me, getting a team in the workplace that can address the problems themselves and in fact do away with a manager might make a lot of sense. So what we found is using the same people doing work with 0.7 reliability, the silo structure produced a 2.5 sigma quality, while the team structure delivered a 4 sigma quality. The manager improved the silo structure by 65% to get 86% reliability from the department. But in a team structure, they improved their departmental performance by 2% to get 99% reliability. It seems that most of the reliability benefits of a team reside with the team and not with the manager. Now, like I said, this supports what I've seen myself across a number of years in industry, and it supports what the Japanese are doing in their operations. And the numbers indicate there's value in having a look at autonomous teams of knowledgeable guys who know enough to solve their own problems and to run processes accurately and correctly every single time. And keep the manager, supervisor away. If anything, make him part of the team. Then the team is where the power is. Now, once we have teams, so when it comes to do my activities, if I have a flow diagram and at some particular point in an activity I've got to make a decision, well, if I'm one human being and I'm under stress or I'm tired and fatigued, then human error is going to be a real issue all the time. But with a team structure, I can begin to call in extra help. If there's no team structure, because the company is designed as a silo, then I will make a choice. But being a human being, I know I'll make many bad choices, even though I think they are good choices. I have no way of confirming my decision is a smart decision. But once the team structure is there, and I'm allowed to call in additional help if need be, that I can go to the manager and pick up the phone and say, Mr. Manager, I'm in this situation here. I've got a couple of options. Can I talk to you about those choices? Sure, come on up. Let's work this out now. And if I can build that sort of company, then I'm going to build a robust, fast-moving, good decision-making vehicle. So yeah, plant and equipment wellness, it's business wellness across the whole life cycle, not just the machines, because the machines are destroyed by the people and the bad choices they make. And I've got to build a process where we have knowledgeable people who are expert in their area and make very good decisions. Then the rest will just happen automatically. This is actually a flow diagram for a centrifugal pump. We have our suction piping coming in, we've got a wet end, we have our motor, our coupling, our bearing housing. And this box, this panel here, is how a pump works. Once I have my equipment and I assign people to look after that equipment in a team structure, then I have an operator watching my machinery. The operator works with the fitter works with the mechanical engineer. I've got a team of expert people. One guy that knows how the machine is meant to be used, one guy that can maintain it very well, and an engineer that understands the complete complexity of the whole process. So now my team contains all the answers. And this engineer is not an office jockey. This engineer comes out of his office and works with the guys in his team. So I can have a silo structure, but I've got to change the focus of the people in those seats to a team focus. So I can now protect my machinery by using teamwork without necessarily changing the hierarchical structure, except the understanding of what I focus on is we work together as a team to maximise the outcome of our plant. And the manager, an engineer helps the operator. If he's not sure what to do, he pulls in as a resource and asks the question. If he's not sure what to do, he pulls in the engineer to write the procedures, to go and do the research, to come back with the right answers. You know, this pump keeps on failing, the impeller keeps on wearing out. Can you find a better material, please? Yes, I'll now go out and investigate and come back with a suggestion of how to solve that problem. If we want our people to own the solution, we want them to be in a structure where that is clearly their responsibility. They have the capacity within that structure to deliver the outcomes. If the operator doesn't know the answer, he has access to an engineer or a technician that does know the answer. And so as a team, the team works with and comes up with solutions. One thing I found as a manager, it's a very satisfying job. Now, your responsibility is to get things happening in the company. And as a manager, you're out there making decisions, putting into place solutions, and watching these come to fruition. And it's as things develop into good outcomes that you feel a great deal of pride in having made those smart choices. Well, the fact that you're happy with your work input and work output should be reflected in everybody's job in a company. The operator too should be happy to come to work and know he's doing top quality work. When an operator has that level of ownership, then we're going to have a lot of problems solved at the shop floor level. The guys will go and look for the answers and the smart choices themselves. They're going to make this process work because they see it as part of their job to make it work. You know you own something when you feel responsible for its final product, final output. When you know you are good at your job, very satisfying. So we need operators that are good at their jobs and understand that what they're doing is the right thing to do. Once other people see you as the expert, see that, hey, this guy knows his stuff, a great deal of respect, a great deal of pride comes across just in our conversations. And if we have the structures in place to support the interaction between people to find the right answers, then you've got an inbuilt culture where the operator owns the outcome of that asset and how it performs and will make those outcomes occur because they can deliver this. They have the process to do it, they have the training to do it, they have the support to do it. So if my company operators don't own the output and quality of what the company's doing, then I know we're not there yet. We're a long way short of what we really want to have as a business. So to start developing operators' competence, we want to develop their competence because it is the competence that earns them the respect that then makes them happier to be in that position. If an operator is not competent, there is no way he'll get that respect. So if I want ownership, I'm going to have to build my people up to be able to do this job properly, correctly, and you and I can see that they know what they're doing. They are experts, and I give them my respect because they are knowledgeable guys. I'll go to them now and ask them for answers. So I want to have companies where everybody from the ground floor up is their expert in their area. And once they're at that level of competence, it's very clear they are good people. I'm happy to work with them. I want them involved in the decision making I've got to make. We mentioned operators, they're always out there. They're part of the solution. Maintenance, engineering, operations, finance. I need all four in the solution for long-lived reliability of my equipment. Now these guys have sensors. They have 5 sensors. And we can employ those sensors as a condition monitoring tool. So we want to use what they know about their plant, and if this guy's an expert in his particular area of concentration, then he's going to know what is right and what is wrong. So I'm going to use my ACE3T checklists with defined criteria. He's going to go around and observe his plant. Same story as Sumitomo Chemicals. The operator becomes a condition monitoring methodology of observing the condition of his equipment. So I want to take this on board as a strategy for our guys to literally be involved with their machines. We want them to use their knowledge intentionally to come up with the solutions to our problems. Not expensive, we're looking for low-cost solutions. We want guys to be physically walking around their plant. The guys that sit behind the computers here and watching the screens, they don't learn much. All they watch for is a little red light or a pressure that changes. Although they're looking for a number, and when a number goes in the wrong place, they action something. They don't actually necessarily understand how that number changed in the first place to become the value that it is. So if I've got guys sitting in control rooms like this, I would be concerned that they don't really understand their machines, their process, and why things change. This guy's different. This guy, over the time, knows why things change because he knows what's right and what's wrong. When it's wrong, he's going to go to his fitter and technician and say, look, this is making more noise. Yesterday it was no noise at all. Today it's got some noise. Can you come with us and have a look at it, please? And we'll work out what's going on. So the operator that walks his plant looking for specific things that are important to know about, he learns what's happening at each individual part of that process over time and with his interaction with other people. The guy sitting behind a computer screen watching the little colours change, I'm not so sure he really understands. He can do his job. He's got the job of sitting in the chair to watch his process. I'm just not sure when the emergency situation arises, when things go wrong and things aren't back where they should be, that he really knows why it happened and what to do about that. So I want to make sure that any process I build, that the guys that run that process can solve the process problems and understand why they occur in the first place. So I guess a snapshot of how we get to that point, what are the criticality, what are the risks, what can cause the failures, what are the conditions that we need to be sure that are monitoring the failures, and if the conditions arise, we're observing of that very quickly. What are the 3 T's that protect against those conditions? What are the proactive things to do to prevent failure in the first place? How often must we go back and observe and do our walk around to detect the beginnings of a problem? We're going to make that then their SOP, standard operating practice. So all these things we decide to do as a team is going to be written down into a document of how to do this thing right. If we do it right, we're going to get the right outcome every single time. So when we find the problem, who do we report that to? If the problem is an issue, what are we going to do in terms of addressing that? So we're going to have to train people to understand what is acceptable, what is not. When it's not acceptable, then we go and raise our hand before it becomes a major problem. We're going to have records of what we record. These guys are going to have a 3T range to be within. We're going to plot that electronically. Being electronic, the whole company can see what's going on. CEO, production manager, maintenance fitters, other operators. So we want to make this public knowledge. We want this knowledge to go and be available wherever people need to know that information. And then, of course, we're going to make this a regular schedule. Whatever we decide to do, the frequency is, that's part of his job. And so in his procedure will be every shift, you will go and walk this part of the plant and come back with this report and type it into the computer to make a record of it. Or it might be every week or every month, whatever is sensible to protect against the risk of failure. The whole idea here is to use the least cost person, the most knowledgeable person for the situation. I don't want to have engineers doing this because that's not valuable for the business. But the guys that know their machines, know their process, and are there all the time, they're the right guys to be doing that level of investigation. When there's a problem, sure, kick it upstairs to a person that can help him technically, but the actual observation we want to do with the people that are there all the time. I should also say this is a manually driven process. As technology develops, a lot of this stuff can be mounted on the machine itself. You actually mount the sensors. When it comes to noise and vibration and temperature, there are sensors out there we can actually mount on our machines. And a lot of companies are having the option of buying a machine, and you actually ask them to option in the sensors for vibration, for temperature, and feed those outputs back to our computer and monitor it 24/7 all the time. So this slide is about using a person because they're typically already there, and it's a low-cost thing to do. You can get this happening very, very quickly. It isn't the only way. You can actually replace a person with onboard sensors and let the computer monitor. This is simply a low-cost way to get something happening fairly quickly. So the guy doing that inspection round, he's going to be asked to, here are the contact points to check for vibration. He's going to have a vibration detector of some type with some sort of readout. On his report here will be a range, that's acceptable range. He goes along, he takes his readings, he writes that down, and then he moves on. Back in the office or back in the control room, he types into his computer, and it is there now as a record of what's happening in the plant. All right, we've talked about the ACE approach, accuracy controlled enterprise. The key word is accuracy. Now, how accurate must things be done to produce the known output that we want? I've done this slide a number of times now, and the message there is not changed. We want outcomes that are within the boundary that gives us the results we're after. So we want to measure the process outputs. Part of knowing we're on the right track is to actually plot this graph, actually plot these numbers, and make sure that it is actually happening. So creating distributions and plotting outputs and monitoring things on a graph is necessary to know that we are in control. And if we're out of control, I want to know that very quickly also. So in lean manufacturing, one of the big pushes that you introduce is control charts. You have control charts. Now, control charts are causing us to measure the process, plot it against a particular range of outputs, and prove the process is in fact in control. So we're going to simply adopt that lean thinking of control charts, but in a fashion that suits the information that we're looking for. Talked about having expert people and knowledgeable people in their area of operation. And the reason we need knowledgeable guys is they know the problems, they know why they occur, and they know the answers. knowledgeable guys have to be trained, and if we don't train people, then we get a distribution of abilities that are naturally out there in the workplace. If I go and hire an operator or go hire a mechanical fitter straight off the marketplace, then I'm going to get a guy come through my door, and he will either have poor skills, average skills, or fantastic skills. I won't expect to see many exceptional guys come through my door. Exceptional guys, the company they work for won't let them go. They'll pay him to hang on to those. So the odds are when I hire a new guy, he's going to be the average sort of skill level. If I want him to be more than average, to be able to do more things better, I'm going to have to take my average guy and make him better able to produce good quality results. So it says to me, if I have a workforce and that workforce produces the results I'm currently getting, and I want to get better results than I'm currently getting, I'm going to have to train the workforce to know how to deliver better results. And that's part of the process I'm going to bring into the company. One of the things I will have to do to make the company better is have people that can make the company better. Either I go and hire a whole bunch of new guys in that have those great skills, or I take the crew I have and improve those skills in the coming months and coming years. Because right now I am where I am today because of the processes I use. And the guys in my business are process decisions I made or someone else made in the past. And that's the outcome I'm getting. If I want to have a better outcome, I've got to have people that can deliver a better outcome. So training becomes an ongoing requirement in improving the wellness of the business. Never stop learning. Challenging guys to stretch their limits, to learn new information, find better answers. So training is part of how we get the control of our processes. Otherwise, I just get what I've already got, and that's got us where we are today. So we not only have an accuracy-controlled enterprise, an accuracy-controlled expert. The guy doing the job is a competent, knowledgeable person and knows what to do well. He's been taught and trained, he's been following procedures, and he will produce these results, the results that we want every single time. So we're going to tie all this thing into a system that includes best practices, because best practices are what we want to adopt very, very fast. We want to use the understanding of our series process number 3, a property, and get rapid change quickly. That means I've got to bring best practice into the company very, very fast. I want to have knowledgeable experts in my business. I want to have standards that produce known outcomes every single time. And I want to find better ways to do what we're doing today so that next year I'm a better company than I am this year. And I want to make this the business system that we work with all the time. So yeah, that's what the Accuracy Controlled Enterprise is all about. Creating a quality management system that takes all these inputs and keeps us moving forward, getting better, ensuring our output is always within the boundary of the quality that we know gives us the results that we're after.